This class is all about modeling real systems. And despite the fact that this course is not focused on modeling systems, there's going to be many times throughout this course I'm going to give you a mathematical model and say, design a controller for this. And you're going to think in the back of your mind, well, where did this come from? Because it's just, it's coming out of nowhere. And so I want to spend one class building up your intuition on how exactly we come to get models that we might use for control. So again, this is not the point of the course, but it does give you lots and lots of important insight about where these models come from, how certain terms appear in the models that we will use, and these all have very important consequences when we come to controlling that system. So this is really building an appreciation for that. And so this first bit of first two slides here is really understanding where modeling fits within the whole paradigm of controlling a system. And so we kind of break this down into the real world and the mathematical world, and that's this big barrier that we have between here. And despite the fact that we live mostly on the right-hand side in this course, ultimately what we want to achieve is we want to achieve impact in the real world. And so what we want to avoid is simply staying in the real world and choosing some sort of best guess or hacking approach. And the problem with this is that these kind of approaches don't come with any guarantees. So the idea of going through a more systematic and mathematically rigorous approach is the fact that we can build out guarantees on how well our design will work. And what's also important is the fact that best guess and hacking is essentially limited to our kind of creative understanding about the system. And so when we go through a more mathematical approach, we can rely on the mathematics to bring out things that we don't already have intuition for. And so much more complicated and much more nuanced solutions can come out of this. So the challenge with modeling, though, is that anything that we do to jump from the real world into a mathematical model is necessarily some sort of an abstraction. There's going to be some aspects about the physical system, the real system, that is not captured in the model. And these could be small things that aren't so important, or they could actually be relatively major things that are important, but are just too complicated to take into account. So there's various different models. So oftentimes we'll be talking about multiple different models that we might use. We might use different models for different purposes. So the same system may have different models depending on how you need to use them. But the idea is that once we have this mathematical representation, which is what we're going to call the model, and in this case, a lot of what we're going to be doing, since they're dynamical systems, will be based on differential equation models. So we're going to use those differential equation models and apply, and this is what this course is all about, systematic analysis and design in order to build out controllers that achieve something like what we want to achieve, one of those 4 control goals. And then ultimately we have to take this mathematical approach and apply it back in the real world, where we hope that this works. And this arrow right here underscores the fact that these robust solutions, so despite the fact that there could be disturbances or there could be inaccuracies between our model and our real system, that the design that we have chosen still works. So again, this is a very rather wordy slide, but the main key takeaway here is that there's no mathematical model that's going to be perfect, and it's not going to perfectly represent what's going on in the real system. But what's really cool about this approach and the whole idea of modeling things mathematically is the fact that approximate models work actually pretty well. In fact, even simple models are still extremely useful. And it's this notion of robustness that brings home this usefulness and allows us to use all of this mathematical framework that we're going to talk about in this course in order to solve real problems, despite the fact that the problems that we're solving are actually more complicated than what we're modeling. And part of key to all of this robustness, and this isn't going to be, we're going to take a break and we're going to come back to this in a couple of weeks when we finally start talking about feedback. But the idea here is that feedback is one of the main mechanisms by which we're actually able to give robustness to a dynamical system. And so that's ultimately what we want to achieve with our controller design. So we're going to talk about primarily one way of accomplishing or obtaining models, and that's using first principle approaches. And so these should be things that slightly jog some memories from past classes, whether it's physics or chemistry or an electrical engineering course. But obtaining models can largely happen either through first principle models or through data-driven techniques. And data-driven techniques are ones that are gaining lots and lots of popularity, and there is lots and lots of applications where it becomes useful. One of the challenges, especially for control, is that data-driven models sometimes make it more difficult to apply some of our mathematical techniques. But there is a large literature, even within control theory, largely called systems identification. And that is really what's used in taking data, or essentially data about the trajectories of the system over lots and lots of time, and inferring dynamics that represent essentially, remember, the dynamics are the rules that describe how a system operates. And so in this course, we won't talk a lot about data-driven models. It's kind of a whole course by itself. Here, what we're going to do is we're going to just focus on identifying how first principle models can allow us to create dynamic systems, essentially identifying the laws by which these systems behave. And so these fundamentally are things like laws of physics and chemistry, stoichiometry, and so on. In order to apply these, we often do have to make some sort of simplifying assumptions. Sometimes we can add some more complicated terms, but oftentimes we do assume away some of them. And ultimately what this yields is some set of differential equations, and typically they're coupled, which means that variables in one differential equation appear in another one, so we can't solve them independently. So examples of things that we'll use: F equals ma, Newton's first laws. We could even use conservation of momentum. We could use energy and mass balance. We're going to use Kirchhoff's laws that describe circuits. So all of these are examples of fundamental laws that describe the rules by which a physical system operates. And those are the ones that we're going to be able to use in order to write down the mathematical model that we can use. So one of the key messages of this video has been the fact that simple models, or any model, is going to be a simple representation of the real system, but that simple models are still very useful. And so one particular set of models that we will study throughout this course is linear models. And we'll understand a little bit more clearly what linear technically means. But you can imagine that for starters, that a nonlinear dynamical system will have nonlinear terms. It'll have sines and cosines. It'll have x squareds. It'll have other higher order terms, exponentials possibly, whereas linear will not have those terms. And so again, we'll get into a little bit more detail about what that means. But despite the fact that we will talk exclusively about linear models, which is one of the simplest approaches you can use, this is what is used by industry, except for maybe some of the most cutting edge industries. Linear models are kind of the backbone, the workhorse of industry. And it's almost ridiculous how well these models work and our control system designs. It's really remarkable what they're able to accomplish, despite the fact that our models are oftentimes very different from the actual system. So again, we will talk about linear systems. It would be easy to poke holes at that, except for the fact that they work pretty well. There is an exciting large literature on more advanced techniques for nonlinear systems. And one of the key things before you get there is understanding what you do in the context of linear, because everything we do for nonlinear is oftentimes an extension of what we do in this class. So with that, we're going to dive into a number of different examples about how we develop models using these first principle bases, and how we extract a linear model from that, and how that represents a real dynamical system. In this activity, you're going to derive the ODE model of a simplified car suspension model. So in this case, mass 2 here represents the mass of the vehicle. The mass 1 represents the mass of the combined wheels and axle system. The suspension, so these springs and dampers here are represented by the spring and the damper here. And then the wheel has some springiness, and that's represented here by the wheel. And so one of the kind of interesting things is, even though the car is moving forward like this along the road surface, this velocity really doesn't have a whole lot to do with anything that we're going to model in this particular activity. But the interesting thing here is that as the car moves, this reference, so essentially the road surface here, is possibly going to not be flat. So you can imagine you have a pothole, you have a speed bump, you have any sort of irregularity in your road surface. That is actually what's stimulating this whole system. And so if this road surface was completely perfectly flat, you're on those salt flats, then this system is going to essentially reach its resting position, and it will just kind of stay there. So nothing's going to happen. So it's actually the action of this reference, this R value changing up and down, that then jostles and manipulates what happens in this combined system. So this often takes students a little bit of time to kind of puzzle this one out. If you're having a really hard time getting through this one, what I'd recommend is going back and taking a look at that vertical spring mass damper example. It is very similar to this particular activity, but now we have this extra mass and a coupling term. So I'll give you a few moments. I really recommend that you try to solve this one all by yourself and then take a look at the solution. So solve this out, chat with some friends, and then move ahead once you've done that to compare with my answer. All right, so you've managed to make it through. Very similar to the vertical spring mass damper. The key idea here is to first draw your free body diagram. In this case, we have two masses. So in this case, I've got mass 1 up here, and so that's this bottom mass. And again, the really important thing when you're dealing with these free body diagrams is to make sure you know which direction you're drawing your arrows, and kind of be purposeful about that, and then think about what it means for these variables x and y to either be positive or negative. So the arrow here indicates that y being positive goes up, and this arrow means that x being positive also goes up. And so what you want to think about is, what are the forces that this block is going to feel when x becomes positive? So when x becomes positive, you're going to be stretching this kW spring. So it makes sense that the force then would be pulling down. And so that's the reason why I've personally made that choice to put that down, and then write the force such that when x is positive, that's a positive force. So now the positive x direction then pulls this block down. Likewise, we've got the spring force and the damping force. These are actually going to pull up. And in this case, these are going to pull up when y is positive. And so that's why I've written these as pulling up, and y is my first term, that it's positive. So again, if you wanted to, you could switch these arrows around and then switch these two and essentially make that, for example, x minus y, but with an arrow going down into the block. So that's essentially the same. So once you have your free body diagram, the beauty is that now you can say that it's the mass times the acceleration. So the variable that's describing this block is x, so it's x double dot. And that's going to be the sum of all the forces on this. And so in this case, if the arrow is pointing down, that's pointing in the opposite direction of x, that means you're going to have this minus sign. If these are pointing up, then that means that this force provides an acceleration in the positive x direction, and so these come in with positive signs. But what you should be looking for is the fact that the damper causes these derivative terms, and the springs should not have derivatives on them. And in this case, it makes sense that the force on the spring down here is going to be related to the difference between x and r. And here, the spring and the damper, this is going to be related to the difference between x and y. So again, if x and y move together, and they move the same amount together, then there is no change in the force here. But if x and y move and y is getting bigger and x is staying the same or not changing very much, then that means that this is, say, stretching the spring and stretching the damper, and so that will cause forces. So similarly, you can write your block diagram or your free body diagram for mass 2. In this case, it just has the two forces that are attached at the base here. In this case, I'm going to write it using the same term, so it's ks times y minus x. And so here then I've placed the arrow going down because as y gets bigger, that's going to stretch this spring and pull the block back down. And the same thing happens here. And so the important thing about a damper is that this is really describing resisting the rate of change of y and x. So these are relative velocities, not relative displacements. So again, these both enter going the opposite direction of y, and so they both come in with this minus sign, and you set that equal to mass times acceleration. So what that gives us, if we just do a little bit of reorganization, pulling the double dot terms to the left, then we can rewrite this, and we're going to see why we rewrite it later, but we can rewrite this like this. But you could leave it essentially in these two equations as well, and that's a very valid model. This particular description sets us up for doing some stuff that we'll do in the next classes. This is a quick reminder on how to model rotational motion. So there are no new Newton's laws. It's simply F equals ma applied in a rotational setting. So instead of force is equal to mass times acceleration, the force we talk about are now moments about a center of mass. And so it's the sum of all those external moments, just like it's the sum of forces. And instead of mass, now it's the moment of inertia. And so that is something that depends, as you know from previous classes, that's something that depends on the shape of the object, whether it's, let's say, a long bar or a flat disk or something like that, a sphere. And then finally, the angular momentum, which is the second derivative of the angular position. So just as a simple example, so in this case, we could model a satellite's attitude, so its angle with respect to some particular reference, and we could use variable theta to describe that. And so in this case, theta could represent the angle from this reference such that aligns that way. Moments could happen due to, for example, this gas jet could essentially create a force that pushes the satellite like this, and that would induce a rotation, this clockwise rotation. And so the way that you would identify that moment is simply just that force applied at that distance. And so that's the force multiplied by that distance gives you the moment. And then you could also have some other moments that could be either due to other gas jets or, for example, in this case, some sort of disturbance moment, and that would also add to it. And so this combined would then be your combined moments. you would then use your moment of inertia, and then you would have your second derivative of your position. And so just like the previous examples where we had F equals ma, this gives you a second order differential equation that then models that system. In this activity, your goal is to derive the differential equation models of the circuit using Kirchhoff's current and voltage laws. So go ahead and press pause and work through this activity, discuss with your friends, and then take a look at my solution. So there are many ways to approach a problem like this, but I'll show you one of my preferred approaches. So one of the important things when you're looking at these Kirchhoff and voltage and current laws, especially the current law, is that there are equitable ways of drawing the circuit diagram. So in this case, we have this source, and then we have this branch that extends into all of these. And one of the things to keep in mind is that these wires effectively, they're all connected, and so they all have this same amount of current and voltage going through them. So really the idea is that this is connected, and at some point in time this branches into the inductor, into the capacitor, and into a resistor. And then these all connect. Let's see, so these two connect and go back to the source. This one actually goes forward and then splits into the second capacitor and the second resistor. And then these come back together and come back. And so this is another way of viewing this, and this kind of helps identify the fact that this first current separates out into IL, I1, and I3. And that's maybe a little bit easier to see in this version of the diagram than the original one. Similarly, this means that IL enters this junction and separates out into I2 and I4. And so looking at it this way kind of helps us identify some of these Kirchhoff current laws a little bit easier. So like we were just mentioning, we can identify those circuit laws, namely the current laws, pretty easily. And that is these two expressions that we used before. And again, that's really just looking at the current splitting into other currents. Now, one thing to kind of keep in mind before we use our next Kirchhoff law is simply just to understand what we expect in terms of differential equations here. In this case, we have two resistors, two capacitors, and one inductor. The resistors are essentially, because their circuit law is just V equals IR, this is a static relationship that does not have a differential equation as part of it, whereas the capacitor and the inductor have derivatives involved. And so each of the resistors will not contribute a differential equation, but you can kind of think about each of the capacitors and the inductor as being a dynamical element, which is essentially introducing a derivative or a required derivative in order to model what's going on. And so for that reason, we expect to have three differential equations that come out that describe this circuit. So we can kind of have that in the back of our minds as we go through this, knowing that that's where we're moving. And so this comes out after we do some of the substitutions in this case. So for example, these two first equations don't have any derivatives in them yet, and that's because we haven't substituted in any of the remaining circuit identities. So our last observation, which allows us to essentially write down some equations, comes from Kirchhoff's voltage law. And one of the reasons that you can see that this is interesting is the fact that effectively this inductor splits the circuit into this part over here and this part over here. And those are in parallel with each other. So you can imagine these guys are in parallel with these guys, but there is this inductor in series in between. And so one of the ways to find this expression is simply just to, for example, take this particular loop. So you could take a number of different loops. You could take this loop instead if you wanted to, but this one's the easiest. This one that's in the middle here, this one's the easiest and allows us to write essentially V1. So we can go against the current and get V1, and then we can go with it to get across L, the inductor, and then across the capacitor. So that means essentially that the signs will be different between V1 and VL and V2. And so notice it doesn't matter if you have minus V1 plus VL plus V2. So the important thing is the difference in sign there. So now that we have these Kirchhoff relationships written down, now the problem reduces to plugging in identities that we know. And so, for example, we know the current across the resistor. We can substitute the V equals IR to get this expression. We know the current, how to express the current here in across this first capacitor by using the capacitance times the derivative of the voltage across that. And then in this case, IL, so IL is something that we could substitute for, but because the expression for the inductor looks like VL is equal to LIL dot, so the derivative of IL, it's more difficult to use this as a state, use IL as a state. So instead we want to we're interested in keeping it as a derivative and then thinking about that element that has the derivative on it as the state. So in this case, we're going to keep IL there. So in the second equation, we can also keep IL around and then substitute in for I2 for the capacitor. Again, we get that form, and then the resistor here. So by the same logic as what we just talked about with IL, we can look here and notice that V1 appears with a derivative. And that also implies that V1 should be one of the states because now we're going to take a derivative of it. So we won't substitute in for V1. And then the same thing happens here, and this says that V2 has a derivative on it, and so that should also be one of the states of our system, and so we're not going to try to substitute in for that if that appears in an equation. And so that's what happens down here at this last equation. We have VL, for which we have this expression and can substitute in LIL dot. And the reason why we're motivated to do that is because VL is not one of our states. We've chosen this IL as one of our states because it's what we've taken a derivative of in the inductor relationship. So in this case, this is VL, and then we've already decided that V1 and V2 are our states, and so now we can just write V1 and V2 and keep them there because those are our states. So again, our dynamical elements for this circuit are the two capacitors and one inductor. And so for that reason, it makes sense that the voltages across those capacitors are our states because those are what we're going to have derivatives on. We're also going to have a derivative of the current across the inductor. And so that's going to be another one of our states of our system. And so then what is it that's driving this circuit? What's driving this circuit is the current that's being applied. And so if that current were to change, then that means that the dynamical elements of these capacitors and inductors would then alter due to that. So these are the system of differential equations that describe this circuit being driven by the current I, which is located right here. Eventually, in a subsequent class, we'll rearrange these into a kind of more usable framework or format, but for now, this is a perfectly fine way to leave this, this set of differential equations. And again, it's important to note that they're coupled in the sense that the derivative here is on V1, the derivative here is on V2, the derivative here is on IL, but all of these terms are in all of these equations, which is what makes them coupled. This activity gives you another opportunity to derive differential equation models for a circuit. I think one of the frustrating or challenging things for many students when approaching these kinds of problems is they feel that there's lots and lots of different ways to kind of look at the problem or substitute variables. And so in this particular activity, we're looking at a case where we're going to write the same dynamics from two different perspectives. And so in the first case, the differential equation model the variable of the differential equation model, so the thing that has the derivative on it, is the voltage across the capacitor. And the input then, it will be the voltage source V. In the second model, again, exactly the same system describing the same dynamics, but the variable that we'll be interested in is different. And so the variable, or the thing that has the derivative on it in the differential equation, will be the current going through the resistor 1. And so these are two different perspectives of the exact same dynamics. So go ahead and solve this out, press pause, and then we'll look at this in a second. So like in many of the cases, one of the first things you can do if it's not immediately obvious is to redraw the circuit model. So if you have the voltage source, you could draw this as resistor 1. And then this breaks into the capacitor and another resistor. And so this helps to identify that resistor 1 is in series with the parallel branch that includes the capacitor and the second resistor. So this helps identify a little bit better, and I think that's easier to see the branching that happens in the current law. And so if we call I the current that's going across the first resistor, and then I1 and I2 the two branches of the parallel, that means I splits into I1 and I2. And so that's what the Kirchhoff's law, current law, shows here. And for the voltage law, we could choose either of the two loops or both of the two loops. In this case, it turns out we just need one of them. So in this case, we're going to take the loop that goes through the capacitor like this. In this case, the question asked for the voltage across the capacitor. That ends up being the same as the voltage across the resistor. So in the end, it doesn't make a difference which loop we end up taking, because it's both going to be in terms of what we're calling V2, which is just that voltage across either of those parallel branches. So from the current law, we can, so again, in this particular example, we have been asked to find the equations with respect to what we're calling here V2, the voltage across the capacitor. So V2 is now our variable of interest, and so we don't want to get rid of that. That needs to stay. So what we're interested in doing is writing everything else in terms of V2, except for the input, which is V. So V can stay and V2 can stay. Everything else needs to get replaced in terms of dynamic variables. Things like constants like R1 and C and R2, these can also stay because they describe the system. So starting from the current law, we can attempt to start to combine and simplify these to get rid of these other terms. And so again, one of the things to think about is the fact that in this circuit, there is just one dynamic element. So there's one capacitor and no inductors. So that means that there should only be one equation which describes the dynamics of this circuit. So since we have these two equations from the current law and the voltage law, we know that we're going to be combining them. And so you can see that an opportunity to do that is that there is one of the variables we need to get rid of here is I, and it's also here. And so if we solve for this and plug it in here, that helps us eliminate one of our variables. And so then the remaining two things to do is to replace these two variables here. So I1 is the current across the second resistor, And so we can just replace it with V equals IR, and that gives us the V2 that we need. In the case of I2, this current is actually the current across the capacitor, and so its circuit element relationship gives us the derivative of V2. So again, gives us V2 what we need to know. And so now we can substitute that in this position for I, and that will finally get rid of all of the other variables and leave us now here with an equation that is entirely in terms of V2. So all of our terms are V2. This one came here, and this term exploded into both of these terms here. And so now, notice again, the derivative is on V2, so that connects and that agrees with what we set out to do, which is to make V2 this state of this differential equation. And in this case, again, that's being driven by changes, for example, in the input voltage V. And so if we wanted to, we could combine these two things together to get this resulting differential equation. Now, when we solve it with another perspective, so from a different variable being the state, we don't expect to get the same dynamics because that variable may vary different than this voltage does. So let's take a look at that case. In this case, we're interested in deriving differential equations where the state is the current across resistor 1. And again, that's the first element that's in series, and then there's the two elements that are in parallel, R2 and C. So again, we can write down the same current law. Nothing's actually changed about this problem. In this case, it becomes useful to write down both versions of our Kirchhoff law because they end up not being completely redundant in this case. So we'll write one voltage law that goes around this circle and another one that goes around this circle. And so this one describes the voltage across the source, across resistor 1, and then across resistor 2. And so that gives us this Kirchhoff's voltage law. The one that goes through the capacitor yields this relationship. And so we could decide to go ahead and plug in for V2, but remember, in this case, V2 is harder to use because our circuit relationship for the capacitor is that I2 is equal to C times dV2 dt. So it's difficult to use this and substitute in here for V2 using this equation because in this equation, V2 appears as a derivative. So let's hold off on that and wait. So in this case, we're interested in remaining only with the variable I. So we're going to try to get rid of I1, I2, and V2, leaving only the state I and the input V. So our goal is to slowly get rid of these terms. So we can get rid of I2 by substituting in the circuit relationship for the capacitor. That doesn't help us too much in the sense that we've gotten rid of I2, but now we've introduced V2. However, we do have an equation down here that includes V2. And so this is how we could end up using this Kirchhoff's voltage law, is to get rid of this voltage 2. And so right now we can just rewrite it like this. So this is still something we need to remove and rewrite in terms of the current I, which is the state we want. And so that's what we're going to do down here. So we're going to take this expression right here, and we're going to rewrite it in terms of V, which is fine to keep, and I, the current, which is also fine to keep. And so now, to substitute this into here, which is what we're doing here, substitute this into here, we actually need to take the derivative. So now we're getting the fact that V2 dot is equal to V dot minus I dot R1. And so the reason why I have it written down here is the fact that now we're taking this voltage law and taking it and substituting in I1 from this relationship. So I1 gets plugged in here, which leads us to this equation. And then that's where, in this case, in the slide, I'm doing the substitution for V2 dot. And so that's going to be this. So I'm going to substitute this V2 dot into there. And that's what gives me this kind of rather long equation where I've just kind of rearranged some terms. We can rearrange it a little bit more now to specifically gather some terms in terms of, again, I is the state. So we're going to have a derivative. It makes sense that we have a derivative on I. And one of the interesting things, we haven't seen this very much yet, but this is an input. Our input is the voltage V on the source. And in this case, the dynamics that describe the current across the resistor require us to also have information about the derivative of the input. So that means that the evolution of the current I is driven not only by the voltage V, but by its derivative as well. And so that's something that we'll see more and more throughout the course, but it takes more sophisticated systems to see that. So this activity can seem a little complicated, so I recommend going through it a few times to better make yourself feel better about choosing different variables as the output, or as the state. Eventually we're going to call it the output, but the state of the system that we're interested in modeling. So this differential equation is describing how I changes over time. The previous one was how V2 changed over time. So it depends on what we want to see, we can derive the model appropriately.